Okay, so again, we may want to do this by examination. We know that the identity times x is always equal to x, and we think of that as the scalar 1 times the vector x. And what you notice is therefore that 1 seems to be an eigenvalue of the identity matrix. And then if you ask the question, what are all the vectors associated with that eigenvalue, you again end up by examination with the span of 1, 0, 0, 1, the unit basis vectors. Why? Because any vector satisfies that the identity times x is equal to 1 times the vector x. Or we could do it this way, where we subtract lambda off the diagonal. If we then ask the question, under what circumstance does this matrix become singular? Notice that that's singular if and only if you end up with zeros on the diagonal, and that only happens when lambda is equal to 1. And then you can look at the matrix 0, 0, 0 and ask the question, when is this true? And you find out that that's true for any vector, and therefore you can characterize this by looking for two linearly independent non-zero vectors, and the vectors are the vectors 1, 0 and 0, 1, although there are many other choices. Okay, what do we have here? What we're plotting is the vector x, which is actually in red, and a thick red arrow points to it, except that we also have a thick blue arrow that points to a times x, and obviously x and a times x always point to the same point, and here we're taking the points to be on the unit circle. So notice that there's not that much interesting to see here, because x and a times x always point in the same direction. Or maybe that is very interesting. It means that any vector that points to a point on the unit circle is actually an eigenvector. So now let's look at diagonal matrices, and here is a 2 by 2 diagonal matrix. Why don't you go and contemplate for what scalars lambda and what vectors x this holds? You will see me in the next video.